Dear learners, welcome to the course Electromagnetic Fields. In this video, I am going to talk about spherical coordinate system. In the previous videos, I have explained Cartesian coordinate system and cylindrical coordinate system. But the spherical coordinate system, we have no two-dimensional coordinate system to help us understand the three-dimensional spherical coordinate system as we have for the circular cylindrical coordinate system. In certain respects, we can draw on our knowledge of the latitude and longitude systems of locating a place on the surface of the earth. But usually we consider only points on the surface and not those below or above ground. Okay. Let us start by building a spherical coordinate system on the three rectangular axes x, y, z. So you shown in this figure. First, we define the distance from origin to any point as r, the radial distance r. The surface r is equal to constant sphere. The second coordinate is an angle theta between the z-axis and the line drawn from the origin to the point in question. The surface theta is equal to constant is a cone, and the two surfaces cone and sphere are everywhere perpendicular along their intersection, which is a circle of radius r sin theta. The coordinate theta corresponds to latitude, except that latitude is measured from the equator and theta is measured from the north pole. The third coordinate phi is also an angle and is exactly the same as the angle phi of cylindrical coordinates. It is the angle between the x-axis and the projection in the z equal to 0 plane of the line drawn from the origin to the point. Thus, the three coordinates of a point P in the spherical coordinate system are r, theta, phi. The range of variables are r is from 0 to infinity, phi is 0 to 2 pi, and theta is 0 to pi as half angle. So now this point P, r, theta, phi can be represented in the spherical coordinate system as shown in this figure. This is the point P. The point P can also be defined as the intersection of three surfaces in spherical coordinate system. These surfaces are r is equal to constant, which is a sphere with the center at the origin, theta is equal to constant, which is right circular cone with apex as origin and axis is z-axis. Phi is equal to constant is a plane perpendicular to xy plane. So now the intersection of these three surfaces defines a point P. Similar to other two coordinate systems, there are three unit vectors in the r, theta and phi directions denoted as ar vector, a phi vector and a theta vector. These three unit vectors are mutually perpendicular to each other. And these three unit vectors are shown in the figure. The unit vector AR is directed from the center of the sphere, that is origin, to the given point P. It is directed radially outward normal to the sphere. It lies in the cone theta is equal to constant and phi is equal to constant plane. Next, the unit vector a theta is tangent to the sphere and oriented in the direction of increasing theta. It is normal to the conical surface. The third unit vector, a phi vector, is tangent to the sphere and also tangent to the conical surface. It is oriented in the direction of increasing phi. It is same as defined in the cylindrical coordinate system. Hence, vector of point P can be represented as P vector is equal to PR AR vector plus P theta A theta vector plus P phi A phi vector, where PR, P theta and P phi are the vector components of spherical coordinate system. Let us consider a point P, r, theta, phi in a spherical coordinate system. Let each coordinate is increased by the differential amount. The differential increments in r, theta, phi directions are dr, d theta and d phi. Now, there are two spheres of radius r and r plus dr. Similarly, there are two cones with half angles theta and theta plus d theta. There are two planes at the angles phi and phi plus d phi measured from xz plane. All these surfaces enclose a small volume as shown in this figure. The differential length in r direction is dr. The differential length in phi direction is r sin theta d phi. The differential length in theta direction is r d theta. Hence, the differential vector length in spherical coordinate system is given by dl vector is equal to dr ar vector plus r d theta a theta vector plus r sin theta d phi a phi vector. The magnitude of the differential length vector is given by modulus of dl vector is equal to square root of dr square plus r d theta square plus r sin theta d phi square. Hence, the differential volume of the differential element formed in spherical coordinate system is given by dv is equal to r square sin theta dr d theta d phi. The differential surface areas are shown in this figure. The first differential surface is ds vector normal to r direction. ds r vector. ds r vector is a differential vector normal to r direction is r squared sin theta d theta d phi. Similarly, the differential surface normal to theta direction is r sin theta dr d phi. Next, the differential surface normal to phi direction is r dz d theta. Next, we are going to talk about the relationship between Cartesian and spherical coordinate system. Consider a point P whose coordinates are x, y and z, while the spherical coordinates are r, theta and phi, which are marked in the figure. Looking at the xy plane, we can write x equal to r sin theta cos phi and y is equal to r sin theta sin phi, z is equal to r cos theta. Hence, the transformation from spherical to Cartesian can be obtained from the equations x equal to r sin theta cos phi, y is equal to r sin theta sin phi and z is equal to r cos theta. Now, r can be expressed as x squared plus y squared plus z squared is equal to r squared sin squared theta cos squared phi plus r squared sin squared theta sin squared phi plus r squared cos squared theta. We simplify this. Finally, we will get r is equal to root of x squared plus y squared plus z squared, while tan phi is equal to y by x and cos theta is equal to z by r. As r is known, theta can be obtained. Thus, the transformation from Cartesian to spherical coordinate system can be obtained with the help of these equations. R is equal to root of x squared plus y squared plus z squared. Theta is equal to cos inverse z by root of x squared plus y squared plus z squared, and phi is equal to tan inverse y by x. We should remember that r is positive and varies from 0 to infinity. Theta varies from 0 to pi radians, that means 0 to 180 degree, and phi varies from 0 to 2 pi radians, that is 0 degree to 360 degree. I hope you could understand spherical coordinate system very well. Thank you.